Thank you, everybody. It's funny how the context of a presentation changes depending on what happens before it. And I think this is quite different to what I imagined this presentation to be, actually. But maybe it'd be useful to think about the slides that I show actually in the context of the two presentations we've just heard. Because, yeah, I think from one angle, the point about the consensus between climate scientists, I think is a really interesting one, and perhaps the sort of some of the slides that I have on the biases that we have in our models, and when we accept that a tipping point has occurred in the impacts information, and then what that means consequently for people, I think is a really interesting discussion to have. But so, yeah, maybe I would say let's try to keep in mind the two previous presentations when I show you some of these more technical, sciencey plots around some of the work that we've been doing in TipESM. Okay, so ooh, they moved automatically. How did that happen? Oh, I didn't touch it though. Okay, so basically, I lead work package 7 in TipESM, which is the work package that looks into the impacts associated with climate tipping points. So what are the societal and ecosystem effects of climate tipping points? So the goal is to focus on quite a few different sectors, so that we can give a more comprehensive assessment. So what I'm going to show you basically is some work we've been doing looking at the subpolar gyre, following Didier's paper, and I'm going to look at some of the bias assessments that we've done with UKASM and some of those CMIP6 models, and present a few questions to you that we can maybe discuss. I'd particularly be interested to see how they intertwine with the previous two presentations. So, as I said, the challenge we have, I think, as scientists in general, is to really understand what these critical changes in the Earth system that we're observing in our models, what they may mean for people and for ecosystems, in particular the ecosystems on which people depend. So, thinking about food and water security. Okay, and of course, there's multiple timelines of that as well. There's the immediate impacts, such as heat waves and droughts and wildfires. There's the medium term on a kind of decadal scale of impacts, such as shifts in farming systems and shifts in the frequency of high impact events. But then on a much longer term, we have things like sea level rise and cascades of tipping points, etc. So there's a lot to consider, of course. Right? So this was intended as a slide really to show, what's happened in the past, right? So I think we're all quite familiar with this from Victor's paper in 2021, showing all of the tipping points that we've assessed in the past in the historical record. But of course, the one thing that sets the present day and the future apart from the historical record is that world population back then was very minimal. So we had a much smaller exposure to it. And of course, all the tipping points that we were thinking about and discussing in this meeting are happening in a very different world to what's happened in the past. Okay? And that's particularly important when you look at the projections of world population, even in the next to the end of this century. On the plot on the left is the developed world, but the plot on the right is the population projections for the least developed countries. So, and you can see that obviously the population rise in the developed world is leveling off, but that population rise in the least developed countries, which are typically the people that are most exposed, is continuing to rise. So that's the challenge that we have. So okay, so some of the results that we've started to look at. So basically, pretty much everything here is looking at some very simple impacts indices to start with. So this plot is looking at an index of heat stress. So on the top row, we have wet bulb globe temperature, which is a simple index that considers maximum temperatures and humidity. Okay, so it's calibrated to understand what the effect on people is. Okay, this is versus just a simple temperature on the bottom row, and I bet you can't really see the details of this plot, but essentially what we see is if you just look at temperature, you see kind of the general warming signal is the main pattern. But if you look at the heat stress index, there's a bit more spatial variability. And then you see them actually changing the spatial variability again when you look at the extremes. So if you go from the column on the left, which is just the mean, to the column on the right, which is the 90th percentile, you start to see a more of a regionalized signal. Okay, so here we highlight Western Europe linked to, and North America, Central North America, linked to a decline in the subpolar Gyre, which we found in one model. So we have a bit more work to do to look at whether this is robust, but this is something that we think is a potentially a good line of inquiry, and particularly following previous published results on the subpolar Gyre. And so the next slide was really to highlight a little bit further Didier's results on the subpolar Gyre around precipitation. So I appreciate it's quite difficult to see, but the plots on the left are JJA and DJF precipitation, the 20 years before the tipping point and 20 years after the tipping point. So you can see that particularly around the tropics, there's a wetting in and a drying in different parts of the tropics. So here, this plot is looking at southeast Brazil. So we work quite a lot in southeast Brazil, and this was quite a concern to us because we work with partners in Brazil who are interested in trying to improve disaster preparedness for things like landslides and flash flooding. So we wanted to look at this and understand a little bit more the results. So you can see here the time series that we plotted out from this data. And when you look at the pre-tipping versus the post-tipping, you can just about see why that difference map plays out, particularly when you look at the rainy season. But if you look at the wider time series, there's a real question there about what time series do we use to identify a real significant change. Now, I think the other thing to note here is that there's clearly a transient signal as well. So you've got clearly probably from about the mid-20th century, there's clearly a drying signal as well, which you could probably pull out there. So then the question is, how do you assess your counterfactual when you have a transient world before the tipping? Sorry, no answers really, just questions for me. And then you could argue perhaps that maybe the post-tipping, the precips perhaps stabilizes and while it's higher, is more similar to the historical climate. And of course, what we actually care about are the extremes. So what's our frequency of exceedance of critical thresholds? And if you talk to Brazilians, that's what they would really say is that they're really interested in those really wet years and how those frequencies might change. So yeah, that's more questions than answers, but hopefully it's something that we can think about, perhaps in the context of markets and finances and of perceptions and consensus. But of course, you look at a different part of Brazil, and there's no such trends. So it does get difficult. How am I doing for time? 2 minutes. Okay, right. So we also had a look at the biases in some of these models. And so thinking back to the heat stress example, we looked at UKSM and for the historical period for 1995 to 2015, we wanted to look at the wet bulb globe temperature for the 5% warmest days within that 20-year period, and understanding what the wet bulb globe temperature bias is in that. So generally, you can say it looks pretty good, with a slight warm bias in maybe Western Europe and North America, but generally the patterns look pretty good, disregarding Antarctica, of course. And you know, we've plotted up quite a lot of PDFs to understand sort of the more extreme end of the heat stress index, to understand how well our models do at the extreme heat stress days, such as greater than 32 degrees, which is considered extreme. Of course, the other thing to consider is the area under the area that's exposed to these extremes. So this is basically a plot that looks at the mean versus the area under extreme heat stress on the y-axis. So and again, it's a different context to compare our models to. I'm going to skip over these results just because I think I'm short of time and I want to get to a discussion. And we did a similar thing also with the precip as well, because obviously, you know, precipitation, extreme precipitation and drought is a particularly important thing, especially in highly populated areas such as South Asia, Mediterranean, and other parts of Europe. But again, I think probably the question from all of this is how do we decide that our models are good enough to use, or do we need to apply a bias correction to really understand what the impacts are following a tipping point? So I'm going to leave us with some questions that, to be honest, we could go ahead and discuss these in more detail in one of the breakout groups that I think is linked to this session, and over coffee in our individual project meetings as well. But I think these are some of the big questions we're thinking about at the moment in terms of assessing the impacts of associated with tipping points. So how do we robustly assess, and how long a time series do we need in order to be able to quantify what the impacts of the tipping point are? What is the counterfactual, especially if you have a transient world, and what are the biases, and when do we decide we need to bias correct, and then how do we do it? So that's all from me. Yes, thank you. Okay.